Okay, everyone, let's get started. Good afternoon. Were there any issues with Lab 1? Seems like it went well. Any questions? Good. Everyone get the help they needed in lab? Good. Okay, so today we're going to start the hardware part of the class. I have Lab 2 is posted on Dropbox, and we have a quiz that is due by next Monday, midnight. So you have all week to take it. You can take it twice. It's got 11 questions on it, multiple choice. It covers Risk 5 and the stuff I'm going to talk about today. The second lab is due on October 3rd. Second or third? Second, second. Which is a Sunday before lecture, as usual. Okay, so let's start out, and I want to start by thinking a little bit about what you covered in CSCE 211. So at the beginning of that class, you should have covered Boolean algebra. And if you're like me, when you first saw that, you thought, okay, it's basically a degenerate form of algebra that's in base 2 with single-digit numbers, essentially, right? So, not interested. And then, your instructor might have told you, well, did you know that if you have a Boolean algebra expression and your objective is to determine whether there's an assignment of input variables that will make that expression true, do you know that's the hardest program, the hardest problem a computer can solve? And it's called the satisfiability problem. And you might have been like, that would have been interesting if I was a computer scientist, but I'm a computer engineer, I really don't care about satisfiability. And then you would have learned next in 211 that you can take a Boolean algebra expression and you can convert it into a circuit by taking each one of the and, or, and not operators and converting them into a logic gate, into an and gate, an or gate, or an inverter, right? And then you might have been thinking, okay, this is pretty neat. Not sure how you could build something in practice like that, and strangely, the instructor didn't tell you how those logic gates worked. Weirdly, not mentioned how they work internally, because they don't look like any circuit that you covered in your electrical engineering 221 and 222 courses. Those all had like resistors, capacitors, and inductors, and logic circuits have logic gates, and it's kind of clear how a capacitor works. It's two plates that are separated by a dielectric, but how does a logic gate work? And then finally, in 211, you should have then learned how to take a digital logic schematic like that one, and then for each one of the gates to associate with them with a slot on one of these TTL 7400 series logic chips, and then connect them together on a breadboard through their pins with wires, where each one of the wires on the breadboard matches up to one of the wires in the schematic, right? And then at that point, you probably, again, if you were like me, you would have been like, now this is what I'm talking about. We're actually building something that does something practical, right? This is engineering, finally. So that, that's pretty much the classical flow. The schematic, or the Boolean algebra here, is called the behavioral representation of the circuit because it defines the functionality, the behavior of what the circuit is supposed to be doing. The schematic is the structural representation, which is when you have components or modules that are selected from some kind of a repertoire, a menu of modules that you have in a library of some kind, and that you can instance them, logically instance them in a schematic, and then connect them together with wires. So you're basically selecting devices from a repertoire. Typically that repertoire is comprised of devices that are pre-designed, but that's assuming that you're using bottom-up design, where you're designing designing things and then using those things, as opposed to top-down, which is where you would put things in a schematic that aren't designed yet, and you'll worry about designing them later. That's top-down design. But in either case, the structural representation is still kind of conceptual, because you're saying, well, I'm assuming I have an infinite supply of all these, and I have, I can afford to put all these down, and I'll just put them down and connect them with wires. And then the physical representation is when you associate these logical, sort of conceptual components in the block diagram with physical things and physical units and physical wires, right? So those are the three different, representations of a design. And in this class, we're going to be doing the same thing as you did in 211, except they're going to look a little differently. The behavioral description is going to be in SystemVerilog, which is a high-level programming language. Now you can define Boolean logic very easily, very naturally in SystemVerilog, but you can do more complex things in there as well. And then the structural design, now this one's a little confusing because in the SystemVerilog, you synthesize it with a compiler. So when you compile it, it gets converted into a structural description, into a schematic automatically for you. However, you can also design schematics in Verilog as well. So it depends on how abstract your SystemVerilog could be. Very abstract, where it's like a big logic equation, and then you're expecting the synthesizer to convert that equation into a sea of gates connected with wires. Or you could design your SystemVerilog at a lower level where you explicitly instance gates in the SystemVerilog and connect them with wires. In SystemVerilog, wires are not wires, they're names. They're variable names. Okay, so kind of like SPICE. If you guys remember SPICE from when you took electrical engineering 221, wires were formed by common names, of connections. And the wires were inferred by the SPICE net list. Very similar thing in SystemVerilog. So this structure actually comes from Quartus. This is the compiler we're going to use. So this structure was, I think I compiled it from there. I don't remember where that came from. Might have came from that code. But basically, you start out with code like that, and it compiles it into a schematic. Or you can write SystemVerilog that looks like this, that's structural SystemVerilog, in which case it still gets converted to that into the compiler, but then there's a one-to-one match between the two. And then the physical, in our case, we're using an FPGA. So the FPGA is kind of like, you think of it like a big array of those 7400 series chips that you used in 211, where they all have slots. And then the compiler will take each of these logical components in the structure schematic, and it will associate them with a physical slot on the FPGA, and then set up the wires to make connections through the FPGA fabric, right? And so instead of having to go on a breadboard and plug wires in, it's still being done, but it's being done by the tools. It's being done by CAD tools for you. So you don't have to worry about plugging things in, which is, very frustrating and error-prone. Okay, so, but, again, it's structural, behavioral, structural, and physical are the three representations of the design. So just another slide kind of shows you might have done this kind of design in 211 where you design gates maybe by hand that followed a Boolean logic expression. And in 211, you should have also done logic minimization where you took a more complex Boolean logic expression and kind of minimize it down to make it functionally equivalent but smaller, less gates. And then you map those on, you could use a Carnot map for that, for instance, and then convert it into a schematic, and then you hopefully had the experience of plugging all those wires in and stuff. Now obviously that's not a practical, that's only for classroom use. You could never deploy a practical circuit with breadboards and wires. A modern CPU would require millions of those breadboards, right? And the biggest problem with those is the debugging them. Like you see this big mass of wires, and it's hard to, if there's a bug, it's hard to trace down all the wires to find bugs. And it's also impossible to reuse effort. Like if you design one thing and then you want to reuse it in a more advanced design, it's tough to do that. Whereas a SystemVerilog and all these tools that we're teaching in this class are designed specifically to make it easier to debug and reuse code. Okay, so how does HDL, the HDL works through three principles. And you might have heard of these before. There's this idea of abstraction where when you make a design, you hide all of the details except for the details that are important and relevant to that design, which is why I mentioned earlier when you were in 211, they told you, hey, here's some logic gates. You have a repertoire of logic gates. You have an AND gate, an OR gate, and an inverter, and you can use them. And you're like, well, how do those work? Not important, because the details of how they work, and basically they work with transistors, but the details of how the logic gates work was unimportant to the digital logic design. That detail was abstracted away, right? So that's abstraction. So for instance, like you probably know that digital gates are actually just analog circuits. Digital circuits are built on top built from analog circuits. And then you could build logic on top of digital circuits, and then an architecture on top of the logic. So you kind of build up the complexity by hiding, details that aren't important. That's one way that you can make, these chips now have 1 billion transistors. How do you manage that complexity? Another idea that's very heavily used in hardware description language is hierarchy. And the idea with hierarchy is that you start out by building components, and then you use those components to build more complex designs, and then you use those designs to build more complex designs yet. So you build up incrementally. So if you looked at the HDL that was used to build the latest, ARM processor, you would find that each file in there is pretty small. They're pretty short, probably less than 100 lines of code, each one. Of course, there's a lot of files, but the reason why that together, when you synthesize those, you get these gigantic logic circuits is because of this idea of hierarchy. And then also in that is regularity, which is the idea of you want to minimize the number of modules that you build and reuse them as much as you possibly can. So you might have seen this in 211 too. Hopefully, they had you build an adder, a multi-bit adder, using full adders, which are 1-bit adders. So you take a bunch of 1-bit adders and you array them together, and you can build a wider adder. And then once you have an adder, you can use adders to build a multiplier, right? And you can also use adders to build subtractors. And once you have a subtractor, you can also build a divider. And so you can incrementally build up. So here's an example of that. Like for a CPU may have, multiple processors, and a processor has functional units, and a functional unit might be a floating point adder, and inside a floating point adder you may have a comparator, and inside that comparator you have a subtractor, and inside that subtractor you have an adder, and inside the adder you have full adders, right? So you have this design hierarchy, and if you want to try to reuse things in here as much as you possibly can, and the degree to which you can reuse things depends on how good of a designer you are, frankly. Because if you can reuse components and get as much bang for your buck out of a module, the faster you can design and the more reliably you can design, that you could do these digital designs. Now you might say, well, why, what's the deal with, this hierarchy? Why is this so important? Well, when you read a SystemVerilog file, the first thing in that file is the word module. Every file is a module. And most code that you write in SystemVerilog is going to be structural code where you're taking modules and connecting them with wires, essentially. So everything is a module in Verilog. So it's an important concept, not only to understand, but to try to leverage it. Now, if you're like me and you're a terrible designer, like I'll design the whole CPU in one big module, right? And partly it's because the CPU we design in this class is pretty simple, but also it's because I kind of get lazy sometimes when it comes to creating new modules and putting them in a design, because then you have to connect them. Every time you create a new module and you want to use it, you have to connect it. But a good designer will try to take advantage of hierarchy and regularity as much as possible. So just to quickly review, you guys in 211, you had a repertoire of modules that you could use, which were the classic logic gates. You had things like an inverter or a NOT gate or a buffer. NOT gate is outputs a logical complement of the input. Buffer is just an identity function, and you could represent these with truth tables, right? So the behavior, in this case, the behavior of these is shown both as Boolean logic and as a truth table. And then what's shown above is the module, is what the module looks like as a symbol. that's meant to be used in other designs. So the idea is that you have an internal representation, and then you have the kind of the front-facing interface that's used for other designs that want to take advantage of that module, right? And then you had the AND gate and the OR gate. AND gate has 2 inputs and 1 output, and the OR gate has 2 inputs and 1 output, but they have 2 different truth tables. So now notice that you have an output, and that output might connect to multiple inputs of other gates, right? But it's important that you never short 2 outputs together. So if you had these 2 gates in a design, you can't connect that to that. That's really bad. That's a short circuit. You don't want to do that. It's also called contention, right? Because every module that you have in there will have outputs, and when you connect a module's output to a net or to a wire, that module becomes the driver of that net. And because what ends up happening is that that module will be pulling up or pulling down. There's a transistor in there that's going to pull it up to VDD or pull it down to ground. And so if you have 2 modules that are both trying to output to the same wire, and one of them pulls up to VDD and the other one pulls down to ground, you end up with basically a low impedance path from power to ground, which will sink a lot of current and heat up the chip, possibly damage it. But it also will put that, logically, it'll put that net into the forbidden zone, which is, like halfway between VDD and ground. It'll be an undefined value. So you don't want to do that. Okay, and then we got some other, of course there's the XOR, the NOR. Hopefully you guys remember that stuff. So a logic circuit, just to formally define this, is a component. And this is essentially what you're designing in SystemVerilog. Each SystemVerilog file is defining a module, or also known as a logic circuit. And each one of those has an input, a set of inputs, a set of outputs, which is on the first line of the Verilog file. And then there's a functional specification, which is the body of the module. And then there's also a timing specification, which we don't worry about too much in this class until the end. Well, I'm going to cover timing towards the end of the semester, and it is important when you design for FPGAs and ASICs, but we're going to focus mostly on the functional aspect in this class. We're not going to try to push these things to run faster. Okay, so here's an example of a logic circuit where you have inputs A, B, and C, outputs Y and Z, and then there's this internal connection, N1. Now there's actually only one internal connection, even though it looks like there's more than that, because you can see that A is an input, and it fans out to 2 connections. It fans out to an input of E1 and E2, which are internally instanced modules, right? So you're writing a module, and then inside that module you instance 3 modules. You create like a little block diagram, and then you connect the inputs of the module to the inputs of the internal modules, and then one of the internal modules has an output that connects to the top level output, right, to the Y, and then there's another one, this output here connects to Z. You see, so you have a mixture, you have inputs and outputs, and then you have internal signals. Internal signals are ones that are hidden by that module when you use it. It's abstracted out, essentially. The N1. The only time you see N1 is when you're working on that design. When you use that module in another design, of course, you don't see N1. It's hidden, right? But you do see the inputs and the outputs. Okay, so now this is something that I don't know if they cover in 211. I don't know if they get to this, but in digital logic circuits, there's two classifications of circuits. There's combinational logic and sequential logic. Anyone know the difference? Did you guys cover that? Well, combinational are logic circuits that are memoryless, no memory, which means that their output is a function only of their inputs, or whatever their inputs are at that time. So a combinational logic circuit will have its output updated whenever its inputs are updated, usually after some propagation delay, right? A sequential logic circuit has memory. That memory can be in the form of flip-flops, registers, RAMs, any type of memory. Anything that's internal storage where it basically makes the output be a function not only of the inputs to the circuit, but of the history of inputs, the past, right? Because there's internal, there's memory in there, right? So in lab 2, we're going to ask you to design a 7-segment decoder and put it on the FPGA board. It's kind of essentially like a hello world program for the FPGA, but we're also going to use that module that you design in there for the other labs, because we're going to use it as the main output mechanism for the CPU. That's how it's going to get data out. It's going to go through the 7-segment displays. But in order for that to work, you need a 7-segment decoder, and you might have designed something like that in 211. A 7-segment decoder is where it's a circuit where you give it 4 input values. That's basically a value between 0 and 15, or 0 and F in hex. And then it converts that to 7 output pins that each go to the 7 segments of one of those numeric LED displays. And so that's combinational, because if you update any of the input pins, it's going to immediately update the output, right? And so the output will only be a reflection of the current input. Whereas a sequential logic circuit, the CPU will be a sequential logic circuit, because there's going to be an instruction memory in there, and there's going to be pipeline registers and a program counter. And those are all sequential elements because they have, there's a register file inside the CPU, and register files are RAM. So those are all memory elements, and in that way the CPU will behave differently depending on the past history of inputs that you give it. Okay, so for combinational circuits, so I'll ask you a question on the quiz about these rules of combinational circuit design. And this is mostly just a terminology thing. But it's important to understand this because in SystemVerilog there's a different coding style for sequential versus combinational logic. So combinational logic is where every element in a combinational logic circuit is combinational, and every node is an input that connects, that eventually feeds through to exactly one output. And the most important thing is that the circuit doesn't have any cyclic paths. So you might remember that when you build memory in digital logic, it relies on a cycle. Like it relies on outputs that feed back to inputs. And in combinational logic, you're not allowed to have that, right? Because if you have that, it'll be sequential, right? Okay, and so we'll also be looking at a lot of schematics in this class. Now you might say, wait a second, I thought you said SystemVerilog is a high-level programming language like Java? How do you put a schematic in there? How do you do that? You don't. You have to visualize the schematic, and then you translate that into a textual representation. Now you might say, wait a second, wait, why don't we just draw the schematic in a CAD tool and then push a button and have the CAD tool generate the corresponding Verilog code that implements that schematic, so that way we can think of the design as a schematic and we can actually enter it as a schematic, and we don't have to worry about doing this bizarre conversion in our heads. Yeah, I used to use a tool like that years ago in this class, but I quit because I started working with companies. Started working with companies that did chip design, and no company uses those tools. They all write Verilog code. Doing the schematic capture is like baby mode, easy mode. No serious professional uses that. They all use HDLs. So at that point I switched to just using straight up HDL. The other reason too is that we found when I used to use schematic capture tools, you draw your schematic and you hit generate and compile, and it would say, oh yeah, there's an error in line 174. And you're like, what's line 174? I drew a picture. You know, like how do I, and then you had to go and look at line 174, which was machine generated, and then try to figure out how that related to what you drew with your mouse cursor. It was insane. Like, it was absurd that we had to go through that exercise. So when you write this code and you run it through the tools will tell you, it'll point to a line number, and you know, hey, I wrote that line. Yeah, I screwed that up. Yeah. So anyway, but we'll be looking at a lot of schematics, and in this class, I'm going to basically give you schematics, and you're going to translate them to SystemVerilog, and that's the projects essentially in a nutshell. So you have to understand how to read schematics. So a schematic, I'm sure you've seen schematics before in 211 and 212, but there are some rules for schematics. Not everyone follows them though, but you're supposed to have a schematic is a structure. You're supposed to have inputs on the left and outputs on the right. Not everyone does that, but it's supposed to show data flowing from left to right. Also, schematics, as you add things and connect things in schematics, they very quickly become very difficult to read because you end up with what I call a rat's nest of wires, just wires going all over the place. And it's really difficult sometimes it's difficult to organize those, and you'll see that I try when I draw them in my lecture slides, I try to keep them readable as possible, but sometimes it gets unmanageable. But you should try to minimize wires that cross, okay? But if they do cross, which sometimes they do, if they cross in an X, they're not connected unless you put a dot on the junction, right? However, if they cross at a T, like if you have a wire like this and then you do this, if that happens, that means you're fanning out a wire. Fanning out means you have one wire that you want to go to two places or more. That's called a fan out. So if you have something like that, you don't need a dot, because the only reason why you'd ever have a T structure like that is if you intended to have those wires connected. But if you have a cross, in most cases when you have a cross, they're not supposed to be connected. They're just crossed because we're trying to fit all this stuff on this diagram, right? So, but if you want them to be connected, you put a dot. Now I try to follow those rules the best I can. Sometimes I mess up, and when I catch it, I fix it. But those are the rules that you're supposed to follow when you make these schematics. Okay, so I mentioned this idea of contention. So the most, and I'm emphasizing this because this is the most common bug that everyone will have in this class, is this idea of double driving a net. So in Verilog, much like in SPICE, a net is a named entity which can be connected to inputs or outputs inside the schematic, right? Each net can only be driven, and when I say driven, I mean connected to the output of one output, right? If you connect it to more than one, sometimes you don't even notice it for a while as long as both drivers are in agreement. But when they disagree and one tries to set that net to 0 and another one tries to set it to 1, Verilog has this mechanism to deal with that called contention, and it'll mark that wire in the simulator with an X. Now you might say, well, okay, why X? Well, so you have to think about this for a minute. Verilog is all about digital design. Digital design is binary, right? So basically every signal is 0 or 1, ideally 0 or 1, right? But there's this third value, X, which is for contention. This is to signify in the simulator that you got a problem. And this is, as I mentioned, this is the most common issue that will come up in this class is, you're double driving a net. So this is the third logic value, X. Now, Verilog also does this thing I don't like, where it also uses X for a don't care. You remember don't care from 211? Don't care is when you don't care what a value is and you want to take advantage of that for the optimizer to minimize the circuit. Now you might say, okay, well then how do I know the difference? If I see an X, how do I know if it's a contention or a don't care? Well, it depends on the context. The only way it could be a don't care is if you set it to a don't care in your code. If you didn't write X to that in your code, then it must be contention, right? Or it could mean that it's coming out of a register that hasn't been initialized, which is another usage of X. But usually X is, unless you explicitly set something to don't care, which you should do if you can, because it gives the compiler some more flexibility to more efficiently synthesize your design. But if you didn't put X in, it's usually a bad sign, or it just means that you haven't reset your counter yet. So that's X. Now, Verilog has this thing, and I've never really taken advantage of this, but it has this idea of strength, drive strength. So when you simulate your design and you set a value to 1, you might see ST1 listed, which means strong 1. So there's this idea of a strong 1, a strong 0, and a strong and weak 1, and a strong and weak 0. And that's designed to be able to resolve these contentions. But in this class, we're not doing anything advanced enough to take advantage of that. We're just going to avoid contention altogether. I've never seen an FPGA that's allowed any kind of contention. So I think that strong and weak one thing is for, like, if you're doing ASIC design. Like I said, I've never actually used it for anything practical. Okay, yeah, so here's an example of contention. We have two inverters fighting over the same wire, right? Okay, another value, though, that you see in Verilog is Z, which stands for floating or high impedance. So if you have a circuit and you're testing it and you forgot to set one of the inputs, it's going to come up as Z. So Z is used for, well, it's basically if you forget to set something or if something's unconnected. This can be a bug in your code if you have a typo, like if you try to drive a signal and you put a typo in there. If you misspell a signal name, then you've basically cut the wire. You've disconnected, because if you have two signals that were supposed to be the same connected, shorted, but you put a typo in one of them, then you've disconnected them, you may see a Z. You can also drive a signal to Z if you're intending to make a tri-state buffer, where you want to be able to connect, like if a tri-state buffer is where you can actively disconnect an output. Right, like that happens for bus type things like I²C, like when you have a bus and you want to be able to have a multi-master bus where you want to be able to have different entities drive the wires. You can use Z for that. We won't be using that in our designs in this class, although I still want, expect you to know what it is in case you see it. So Z is high impedance. So to summarize, in Verilog uses 4-state logic. Basically, you could have a 0 or 1 or a Z or an X. VHDL, which is another HDL, I'll talk about that more in a minute. It has some additional, I think it has 6. VHDL uses dash for don't care, and it uses U for uninitialized register. So I think VHDL has 6 symbols. Verilog has 4. I wish Verilog had the U, because I think that's useful to know if you have an uninitialized register. Now, just to be clear though, we're designing Verilog to go to hardware. Once the design gets into hardware, there's only there's a 0 or 1, right? There is no Z and X. Those are only for simulation. That's for when you simulate, when you're debugging and validating your design. Once it gets to hardware, then it's it's purely digital, right? Now, if you have a contention in a hardware circuit, like I said, the signal may go into the forbidden zone and be undefined. But in general, you think of all digital signals as 0 or 1, okay? By the way, you may also hear about this. There's this thing called Verilator, which is kind of a cool tool. You might come across this. Verilator is an open source package that you can get in Linux and Windows. And it will take a Verilog file and it will convert it to an executable format so you can run it, right? Which is kind of neat. It's a useful tool, and it's free, unlike the model sim that we use in this class that's commercial and it's expensive. You have to buy a license. The problem with Verilator is that it doesn't obey the 4 logic level, 4-state logic. It only goes 0 or 1. That's why I don't use Verilator in this class, because Verilator is not, to me, I don't like Verilator because if you double drive, it has just undefined behavior. There's no way that it can signal to the user that you've double driven a signal and you've got contention. And the reason it doesn't do that is for performance. Verilator is designed for performance, to be fast. So this is a trade-off, a compromise they make. They don't allow you to have 4-state logic. Okay, so let's talk a little bit in general about hardware description language. So most of the market share in hardware description language is in 2 languages, VHDL and Verilog, or SystemVerilog, which is kind of a superset of Verilog. It's kind of like the C++ to C, right? I used to just teach straight up Verilog, and then we switched in this class to SystemVerilog because the textbook switched to SystemVerilog, the second edition of the textbook. So we use, if you know SystemVerilog, you can easily read Verilog, and if you know SystemVerilog, you could even figure out VHDL. Now you might say, wait a second, are you telling me that in the history of hardware design, there's only been 2 HDLs? No, there's tons of them. But for whatever reason, unlike regular programming languages where languages come and go, Python or Rust and Go and blah, blah, for whatever reason, it's really bizarre, but even though MIT came out with Blue Spec, it was supposed to be the greatest language, and then it just vanished. No one cares. Berkeley has this thing called Chisel now that they use. It's based on Scala. Oh, it's functional, blah. It'll disappear. These are the only two that kind of persist, and they've both been around for a long time. VHDL was actually the first one, and it has kind of an interesting story behind it. So it actually was developed by the US Defense Department, believe it or not. So back in the 70s, the Defense Department was buying a lot of chips from vendors, a lot of custom chips, for like special purpose embedded chips for anything. They're a big customer. And the problem is that when they would buy these chips, or they would contract a defense contractor, design the chips and then ship them, they didn't have a precise way to describe what they were supposed to do. They would just have to write in English, say, well, this is supposed to control the turn on an M1 Abrams tank, and we're going to give it an input, and it's supposed to control the elevation of the gun, and it was just all very vague, and it wasn't precise, and of course, as you might imagine, the contractors would inevitably send something back that didn't work. So VHDL was originally written as a specification language. It was to basically say, this is the behavior of the chip in a way that is reproducible and is precise, and it's down to the cycle, the clock cycle. And that way, if I contract you to build this chip to control that turret on the tank, it's got to match exactly what the behavior is defined as in this language, right? And then eventually, they started building the simulators for the language, and then the really cool thing came, which was the synthesizers. The idea that you could say, well, here's a VHDL, and I'm gonna lower it straight on down to hardware and just make a chip from that. I could just almost take the engineer out and have it automatically generate a design that fulfills the needs of this description, right? That matches the functionality of the description. Now, so what you've got now is a synthesis and a simulation. In this class, we're going to use those tools. They come from two different companies. We're going to use a simulator called ModelSim, and we're going to use a synthesis tool called Quartus. Two different companies, and they both use slightly different dialects of Verilog. So you may get an error when you compile with ModelSim, and then you go to synthesize it, and all of a sudden it's complaining about something. You're like, what the heck? I worked with the other. So you'll just be aware of that. They're two different tools. And the reason is because ModelSim is the best simulator. It's the industry standard. So if you guys get a job at Intel or AMD or NVIDIA, they're using ModelSim. It's the most well, they have a new version now called QuestaSim, but it's built with the same. Actually, the one we use in class now is we upgraded to QuestaSim. So actually, when you start it, you'll see it won't even say I use ModelSim because that's the old name, but it's called QuestaSim. But basically, it's the standard, and it's the industrial standard for logic simulation, behavioral simulation, for HDL simulation. And then Quartus is from Intel. It was originally from the FPGA company Altera, and then Intel bought Altera. So now it's from Intel. And it's the synthesizer. It's what takes your Verilog and it converts it into a form, ultimately, that you can program the FPGA with. And then the circuit that you design snaps into reality. It becomes realized as a fully working circuit, much the same way you did in 211 when you put those chips on the breadboard and you wired them up, and suddenly you had a working circuit, right? It's kind of like that. Okay, so that was VHDL, and then Verilog. VHDL stands for VISIC HDL. VISIC just stands for Very High Speed Integrated Circuit, so it's a nested acronym. I'm sure they were real proud of that. Back in 1981 when they came up with that nested acronym. And then Verilog was developed shortly thereafter in the mid-'80s in the commercial sector. It was Gateway Design Automation was a small startup company. It was eventually eaten up by Synopsys. They're both actively maintained, and they have about a 50-50 split. To this day, about half the people use VHDL and half use Verilog, and then you've got some weirdos in California that use Chisel, and some weirdos in Massachusetts that use Blue Spec. But basically, everyone's using one of the two, and they're similar. Okay, so I already mentioned that. Okay, so now let's look at some examples here. But quickly, before I get into that, I mentioned that there's behavioral and structural code. Behavioral code describes behavior, and structural code is a schematic that's been encoded, right? you can mix them together. You can have structural code and behavioral code in the same module, right? You might say, well, wait a second, what are the rules, though, for behavioral code? Well, basically, Boolean logic is behavioral. So you could put Boolean logic. Things like state machines, multiplexers, simple multiplexing behaviors that we use a ternary statement for. I'll talk about that in a minute. What else? Basically, anything that can be resolved to a truth table in the end. I mean, it comes down. Now, the thing is, though, is that behavioral code, as I mentioned, is usually the leaf nodes of the hierarchy, right? So that hierarchy that I showed earlier where I had the full adders on the bottom, a full adder is a truth table. And it can also be described as Boolean logic, right? But those are the leaf nodes. That's the very bottom of the hierarchy. As you go up the hierarchy to more abstract nodes towards the root of the tree, which is the design root, the top level node, that's like the top, like the CPU, the product, the final product, that's the top level. Most of the modules in that design hierarchy are all structural. Make sense? So what I'm trying to say is that a lot of the code you guys will write will be, most of it will be structural code, which will be basically instancing things and connecting them with wires and trying to reuse code as much as possible. Okay, so here's an example of a behavioral module. So we have, and this is intended to introduce you to the syntax. The syntax of Verilog is different from anything you've seen before. It's not as unfamiliar as VHDL. I used to use VHDL in this course, and I switched to Verilog. But let me just explain what's going on here. The first line is typically the module line. So you say module, and then you give it a name. That name is what you'll use to instance it. So you could think of that like a class name in Java or C++, right? And then you have your inputs and outputs there. Now there is some variation on how you can write the inputs and outputs. Notice in this case I say input logic. Logic is the basic data type, by the way. So input is a modifier. So I say input logic A, comma B, comma C, comma output logic Y. So the way this works, and this is one feature that you don't see in Java and C++, B and C don't have a type associated with them. And the reason is because they inherit the type, the last type given. So if you say input logic A, and then you say comma B, it's assumed that B is also an input and also of type logic, right? So you only have to specify the type whenever you're changing the type in the list, right? Now, depending on your coding style, you may not like that. If you want the code to be as readable as possible, you probably won't do that, and you would just spell the whole thing out and say input logic A, new line, indent, input logic B, new line, indent. That way it's as readable as possible, right? Because doing it this way is a shorthand, right? It just depends on how like careful you are when you write your code. So I typically use this style, but like I said, I tend to be kind of quick and dirty and sloppy when I write this stuff, more so than I should be. And then notice that at the end of the module line there's a semicolon, which is a little weird. That's not like any other language I've seen. And then at the end of the module it says end module, but no semicolon. Don't know why that is. So you have module, end module, no curly braces here. You typically have like an end, that will define the end, as opposed to a closing curly brace like you would have in C. And then inside the module, there's only one statement, and it's an assign statement. The assign statement is called the concurrent assignment statement or the continuous assignment statement. And it defines a circuit. Basically, it's a logic circuit that assigns y as the output as a function of A, B, and C. And then the operators are all Boolean logic operators. So we've just defined a Boolean logic equation in there, right? That one line of code is a circuit, is a logic circuit, which means that I can't have another line that drives y. Otherwise, I'll have a double-driven signal and I'll have contention, right? So that one line of code controls y. It's also a combination of logic element, which means that y will be updated instantly whenever A, B, or C change, regardless of what else is going on. And for that reason, HDL is referred to as as having concurrent semantics. Because if I had other assign statements in this module, I just have one. But let's say I had 10 assign statements. The order of them would make no difference. I could take the order of them and scramble it randomly, and it would be exactly, it wouldn't make any difference. Now, you can't do that with Java or Python. You take a Python program and scramble the lines of code, and you've broken it, right? But in Verilog, you can do that because every line of code runs concurrently, or every statement, I should say, runs concurrently, because every one of those statements represents a circuit, and circuits don't have any kind of ordering associated with them. There's no like program counter like you have with software because you're making hardware. So there's no place where your code is sort of running at this time. Like, so if you open this in a debugger, there's no current, like instruction pointer in there. It's just everything runs at the same time, right? So it doesn't matter, generally speaking, you can just scramble the lines of code. The only thing it does enforce is it wants you to declare signals before you use them, which you've seen that before in C++. Verilog, for whatever weird, bizarre reason, still enforces that, even though for the most part, order of lines of code doesn't matter. But it still doesn't want you to use a thing and then declare it underneath.
Are modules concurrent as well?
Yes, yeah. So if you instantiate modules as a structural, like instance modules and connect them, yeah, they're all running concurrently. And by the way, just so you guys understand, the modules are just fake. Like, they're just for designers, they're for humans. Because when you synthesize this onto the hardware, it flattens the hierarchy. So when it becomes physical hardware, the modules disappear, right? Because everything gets kind of inlined into one gigantic rat's nest of wires. Which is why, I don't know if you've ever seen a layout view of a chip. Like if you look at the masks that make a typical GPU or CPU, or even if you just see a micrograph, like a photograph of the chip under a microscope, you look at that and you're like, I mean, how would anyone interpret? I mean, it's huge, it's enormous. I mean, you look at a chip under a microscope, it looks like a huge city in there. How could anyone like go in and look at and identify what any part of that chip is doing? You can't. Because the design logically is represented as a hierarchy, and you go, oh, I have a processor core here, and the register file is here, but when it's converted into hardware, you lose all of that, right? And so that's one thing that you should keep in mind is that the hierarchy is there for your benefit as the programmer to organize your files and your designs, and to reuse designs too, as I mentioned. Reusability is a big thing. You can't start from scratch when you design the next generation of CPU. Okay, so when you have this thing then, like I mentioned, you can simulate, oh wait, back up, I skipped that last slide. So the first step here is to simulate. How do you simulate? Do you use print debugging? Can you put a print in here? No. Can you use a debugger? No. You basically simulate it, which when you simulate it, what you're looking at here is an oscilloscope, or a logic. You're looking at a graph where the horizontal axis is time, and the vertical axis is meant to represent voltage, so you have, but it's binary. So you don't have, it's not analog, you just have two voltages. And so it's not labeled 0 and 5 volts, it's just high and low because, well, I don't even know what voltage we might, we could use any voltage to represent a 1. Could be a 1 volt, could be a 3 volt. Doesn't matter, I don't care. I just have low and high, right? So what you're seeing here is you've got A, B, and C, which are the top level inputs that are being driven by an unknown entity. Someone's setting those, we don't know who. Like someone, usually it's a test bench, it's a test harness, it's something that's stimulating those inputs, because in terms of this design, they're inputs, there's no obvious person responsible here for these guys. So someone's setting these guys, and the way they're setting them is through a counting sequence. So the way that you read this is, if you draw a vertical line down through this graph, you're capturing an instant in time. So if I look here, A, B, and C are 0. And if I look here, A, B, and C are 0, 0, 1. And if I look here, A, B, and C are 0, 1, 0. And if I look here, A, B, and C are 0, 1, 1. It's counting, 0, 1, 2, 3. Where the numbers are represented as A, B, and C, where A is the most significant bit and C is the least significant bit. And so I'm adding 1 to the C position, right? And therefore I'm getting a counting sequence. So what I end up doing here is I go through all 8 combinations of A, B, and C from 0 to 7. So there's 0, 1, 2, 3, 4, 5, 6, 7. There's 7 at the end. And based on the rate at which I changed those signals, it took me 800 nanoseconds to go through all those. And then I looked for each one of those input combinations, I looked at the corresponding value of y. And as a tester, I want to make sure that the y is behaving as it should according to the Boolean logic, right? So as a tester, I'm going to be comparing this y to my expected y based on what I know about the circuit, right? Now, do you commonly test circuits like this by going through every enumeration of the inputs? No, because the number obviously grows exponentially with the number of inputs. But for a small logic circuit like this, I can exhaustively test it with every possible input. Now, this is also because it's combinational. Remember, if this was a sequential circuit, then the output would depend on the order of inputs. So not only would you have to worry about every possible input combination, but every possible history of input combinations, right? Every possible sequence, right? So it would obviously, testing in real life is difficult because you, generally speaking, you can't exhaustively test. But that's what you're going to see in Model Sim. You're generally going to see something like this. It's called a timing diagram, and it's meant to represent an oscilloscope. Also, the other thing I want you to notice here is that whenever an input changes, that triggers a change in the output. Like for example, here I had, actually in this case, I had all three inputs change simultaneously, which triggered Y. In this case, I had two changes that triggered Y to change. And in this case, only one. So in this case, A, B, and C were 0. All I had to do was bring C up to 1, and that caused a corresponding change in Y from 1 to 0, right? But notice there's no delay there. These two things, the input and the corresponding, the change in input and the corresponding change in the output happen instantly. Now, in reality, that's not instant. There's a propagation delay because these circuits are capacitor and resistor networks. So it takes time to charge and discharge the capacitances in a digital logic design. And so in reality, you would see a delay between C changing and Y. And we're going to talk about that later in the class when I talk about logic delay, propagation delay, and contamination delay. But for now, when you run this in the simulator, this is being driven, this is a behavioral simulation only, it's technology agnostic. So it doesn't know what the propagation delay is because that all depends on the technology that you're using to implement this. In other words, how fast the FPGA is or how fast the technology node is when you fabricate this on an ASIC, like if it's a 4 nanometer process or an 11 nanometer process. And also there's, you know, the physical distances that are covered and where the circuit, how the circuit is laid out, all of those determine the capacitances in there and resistances, which in turn define the delays. But because this is technology independent, I'm only testing the behavior of this digital logic, you'll see that everything is instant. You'll see these changes happen instantly. You guys with me on that? Now you can go back, by the way, and you can synthesize it and put the delays back in. You can model the delays. I never do that because there's better ways to do that, where it's called timing closure. When you tell the synthesizer, look, I want the critical path delay in this circuit to meet my timing requirement of 400 megahertz, which means the critical path has to be less than 1/400 millionth of a second. As long as you can do that, I don't care about, you know, so if you can meet those requirements, right? That's generally how it works. Okay, so first that was simulation. Synthesis looks like this, where you have the logic here, and it will actually convert it to a gate level netlist or a gate level schematic for you. And the tool will actually do this. You can take your code and you can launch a tool called the RTL viewer in Quartus, and it'll show you the gate, and this actually came right out of Quartus. It'll show you the gate level description. Now this is obviously before it puts it on the FPGA. It's just saying, well, I can make that circuit with that netlist or that schematic. And then when you put on the FPGA, then it has to map each one of these gates to a spot on the FPGA, which is, again, what you did in 211 when you decided which gate to allocate on the 7400 series chips. Of course, you do that by hand, and this process I'm describing is automatic. Okay, so let's talk a few more things about SystemVerilog syntax, because after all, this is just another programming language, essentially, that you're learning. So it's case sensitive, which shouldn't surprise you because all the languages you guys have used are case sensitive. The reason they bring this up in the book, though, is because VHDL is not case sensitive because it was derived from Pascal, which is not case sensitive. So that was another lineage of programming languages that's actually not case sensitive, but Verilog is. You can't start identifiers. Identifiers can't start with numbers, which you might say, who the heck would ever do that? Well, when you're doing hardware design, sometimes it makes sense to do that. Like if you have a 2-input mux, you might want to call it mux2 or 2mux, but you can't start identifiers with numbers, so you should call it 2mux, or I'm sorry, mux2. Put the 2 at the end. White space is ignored. You guys are used to that. And comments use the C++ Java style comments. / is a line comment, and a /*/ is a block comment. Okay, so now let's talk about how you actually connect inputs and outputs to modules that you instance in structural Verilog. So here I've got 2 modules. Now, by the way, these modules generally go in their own files. That's the convention. You don't have to do it that way, but that's pretty much how everyone writes VHDL. Every module goes in its own file where the file name is named after the module. But in this case, I've got them both side by side. So I've got this thing called my design, and I got a thing here called and3. Now, if you were just looking at these 2 modules, you would not know immediately which one is the top level module, which one is more abstract, which one is less abstract. Well, the only way to figure that out is to look at which module uses the other one, essentially. And you can see that my design instances and3. So my design is the more abstract, it's the top level module, and and3 is a leaf node. It's the bottom, lower level, right, module. So my design is here. It has no inputs and no outputs, which is uncommon for actual designs, but it's common for test benches. So if you want to design a test bench that tests, oftentimes you'll design a Verilog module that tests another Verilog module. It drives the inputs and checks the outputs. Those don't have any inputs and outputs, but usually anything else has got to have inputs and outputs, because if the circuit can't communicate with the outside world, then it's not going to do anything useful, right? But in this case, my design has no inputs, no outputs, and it has 4 internal signals, A, B, C, and N1, which are declared internally. You could think of these as like local variables, but in reality, they're wires. And then these wires need to be connected to the and3, which I'm going to instantiate inside the my design. So the syntax here is and3 space and gate. Now this is the crazy thing about this. This AND gate is the name of the instance. I could create another AND3 and name it AND gate 2. But that word, that name, is basically never used for anything. It's essentially useless. The only time you'll see that is in the simulator. If you're simulating and you want to look at the hierarchy in the simulation and drill down, you'll see these names. But aside from that, there's no practical impact of the name on the design, right? It's just a placeholder, essentially. So I have an AND3, which is the module I'm creating, and then I'm going to give it a name AND gate, and hopefully I use more than hopefully I instance more than one AND gate, because that's the concept of regularity. I want to be able to reuse that module as much as I can. Okay, now the next part is a little wacky. So how do I connect inputs and outputs? You have options here. You can do these positionally like you do in Java and C, or you could do them by name, which is what I do here. The advantage of connecting these things by name is that you don't have to remember the order. You don't have to cross-reference the order. And that's important because a lot of these modules are going to have a massive list of inputs and outputs. It's impossible to keep track of the order. So this is the best, most readable way to do it, right? And also, you don't, even as you write it, the order doesn't matter. What I mean by that is, I've got an input here called ABC on AND3 and an output called Y. So I want to connect, let's say I want to connect the output first, Y. So I put dot Y and then in parentheses N1. That connects N1, the N1 wire, to the Y output on AND3, right? So Y is the port. You could think of that as the formal parameter, and N1 is the actual parameter. That's the wire internally that I want to connect to the Y output. And then likewise, I have B, A, and C, which are I deliberately put those out of order compared to what they're listed at up there. But I can connect the inputs. The B input port is going to connect it to the B internal wire, right? So what ends up happening here is that inside this design, the N1 signal is shorted to the Y signal inside this design. So depending on where I am in the hierarchy, that's the same physical. I mentioned that it's flattened, right? When you synthesize this, the design gets flattened. So what ends up happening is that Y and N1 is the same. It's the same wire. It's the same physical wire on the FPGA, but it goes by two different names now because it's called N1 if you're in this perspective, and Y if you're in that perspective, right? So when you simulate, you can look at the design in different perspectives, but you have to keep in mind that there's all this renaming going on across the hierarchy, right? In this case, I gave the same name to those signals, A, B, and C. Just more convenient that way. Make sense? Okay, so does that, you guys follow on that, how you connect those? You're associating a name on the module that you're instantiating with a name that's in the space of the thing that's instantiating it, right? Now there's a way you can do that in Python too. A lot of people use that Python convention. Or you could do it by order, but this, like I said, I recommend highly that you use this syntax when you connect those wires to a module. It's much easier to read. Okay, now by the way, if you forget to connect one, let's say that I didn't put the C on there. What would happen? Well, it would work, except C would be a Z. We'll get the value Z, high impedance. It would be floating, right? And if I had and because it's an input, if it were an output, let's say I didn't connect Y, then it just wouldn't be connected. Y would be, it wouldn't be floating. It would be driven, but it wouldn't be influencing any inputs outside of the AND gate, right? So yeah, you don't have to connect all the ports. Okay. All right, so let me show you another example of the structural code. So this example is a little bit more complex. In this case, I have an AND gate, an inverter, and a NAND gate, right? And the idea is that the NAND gate is the most abstract top-level design because the NAND gate creates an AND gate and it feeds the output of the AND gate to an inverter to create a NAND gate with one internal wire called N0 that connects those two, right? And then I'm going to connect the top-level A, B, and C inputs on the NAND gate to the A, B, and C inputs on the internal AND gate, and I'm going to connect the top-level Y output to the Y output from the inverter. You guys make sense? So this is my NAND 3. That's the port description, the module line, inputs and outputs. And then first thing I'm going to do is I'm going to declare this logic N1. Logic is a binary wire. And then I'm going to instance my AND gate, which I call it AND gate. I'm going to instance my inverter. That's the name I gave it. And then based on the stuff in these parentheses is how I connect all this stuff together. And again, all the connections are made through names. So I've got A, B, and C inputs on the NAND are going to connect to the top level A, B, C inputs on the NAND, right? Likewise, the N1 is now going to be connected to the Y output, so there's a rename happening here. So I have a Y here and a Y here, and I got a top level Y. The top level Y is going to be connected to that Y. The internal Y is going to be connected to N1, right? Which I need to have that N1, that's my glue. That's how I glue those things together. That's how I connect them. And then likewise, A connected to N1, A input, and this Y. So this wire in the middle is actually renamed twice because it's called N1 here, it's called Y inside the AND gate, and it's called A inside the inverter. But when you synthesize this to hardware, it's all just one wire, right? So then when there's a feature in Altera where you can do something called signal tap. You can put a virtual logic analyzer and read these through JTAG, that's the debugging protocol. But when you go in to pick your signals, you have no idea which signal you'll actually see. Because when it puts this inside the final design, it only uses one of these names. There's no way to tell which one it's going to use. So sometimes it's hard to track these wires down after you synthesize if you do use that style of debugging. And we'll be doing that in this class. I'll show you how to do that. Okay, so then let's simulate it. So this is an actual screenshot from ModelSim. So you'll notice it looks a little different. It's got the kind of the dark color scheme. And you you'll see I've got A, B, and C are going through their little counting sequence here from 0 to 7. It actually happens 2.5 times. And Y is correspondingly changed. It's just the NAND. So a NAND is basically always 1 unless the inputs are 1, 1, 1, right? Notice that the Y says strong 1. Ooh, strong 1. I don't know. I don't like that, but that's a Verilog idiom, the strong 1. These aren't strong, but that's strong. Okay, but it's just 1 or 0. Okay, so then another thing you can do, which, as you might imagine, those examples were all single bit. All my wires were single bit. You can easily extend them to multi-bit, right? And that's easy. You basically create an array of bits. You have a logic array. But here's the catch. Verilog has something that I never can get used to. After years and years of writing Verilog, I can never get used to this. When you declare a multi-bit signal in Verilog, they do the most unexplainable thing. They take the size of the array. Well, there's two things they do, actually. The first thing is, instead of just saying 4 for a 4-bit signal, you say 3:0. Means 3 down to 0. 3, 2, 1, 0, 4. Why can't you just say 4? Why do you have to say 3 down to 0? And I tried to reverse it, by the way. If you say 0:3, it makes no difference. Of course, the convention most people use is the bigger number first, then the smaller number. But you can put 0:3 too. You just can't put 4. It doesn't like that, right? If that weren't bad enough, that number goes before the name of the variable. So if you want to declare A and B as a 4-bit inputs, you have to say logic bracket 3 down to 0 bracket AB. I never get used to that because in every other programming language that has arrays, you put the brackets after. You'd say, put the size after after the name, not before. Verilog puts it before. I don't know why they do that. I think they do that because the logic 3 down to 0 is like the type name. It's like a 4-bit type. I think they try to associate the logic and the size as one monolithic thing before you get to the name. But it's so much different than any other language, it still screws me up. I always mess up and put it after, and then I get an error, and I got to go back and fix it.
Worse is that you put the brackets after the variable name, and you put an array.
Yeah, well, so one of the things we're going to do later is we're going to create a RAM. A RAM is like a 2D array because there's a width and a height. And the width, and this even gets more confusing because in a RAM, you put the width first, and then you put brackets after the name to create the depth, the number of entries in the RAM, which is even crazier. And what's even crazier about that still is in C++, you put the rows and then the columns. But here, if you're putting the width and the depth, it's reversed. So not only is the order, the bracket positions weird, but they actually switch logically the dimensions of the 2D array in Verilog with respect to C or Java. But anyway, yeah, we'll get to that. But for now, we're just using multi-bit signals. You could think of them as a 1D array, right? Now, the nice thing is that in this case, I've got all these 4-bit values, and I'm using these Boolean operations, and they're treated like bitwise operations in C or Java. So you guys are already familiar with how bitwise operations work. Tilde is a complement, bar is or, ampersand is and, caret is XOR. Those are all traditional binary bitwise logical from other languages. Any questions about that? Okay, so let's look at another. Now this is another example, but this is something this is hugely important because you use this all the time. So there's this operator called the ternary operator, and it actually exists in Java and C. I don't know if Python has it. Probably does, but ternary operator is basically a question mark. So you have an expression, question mark, right? And then what follows the question mark is what the expression should evaluate to if the condition was true. And then you put a colon, and then whatever comes after the colon is what the whole expression evaluates to if the initial condition was false, right? So you have this in Java, C, C++, but almost no one uses it in those languages. It's very uncommonly used. But in SystemVerilog, it's used everywhere because it's the way you build a multiplexer. You guys remember multiplexers? Hopefully you covered multiplexers in 211. So a multiplexer is basically the way, remember I said you can't double drive a wire. You can't have two drivers on one wire. So the question is, wait a minute, if that's the case, then how do I implement a fan-in? Meaning that I need to have two possible values or more that can go on a single wire. But you can't drive a single wire at the same time with two different values. You get contention. You blow up your chip. So what do? Well, the answer is use a multiplexer. A multiplexer is a way that you can select what value you want to put out on a wire, and then you can choose between as many values as you want, right? So a multiplexer is usually shown as a trapezoid here. And by the way, multiplexers are the basic data path element for CPUs. This is the way that a CPU can route data. That's why you can choose between adding two registers or add a register to memory. Or do I want to compare two registers or compare a register with 0? Right? Or do I want to add a register with an immediate, or do I want to add a register to another register? All of that is done with multiplexers. All of those decisions internally inside the CPU are all implemented with multiplexers. Make sense? So a multiplexer in Verilog, in a symbol, it's just a trapezoid. So you have a select bit on the top, two inputs on the left, one output on the right. The select determines which of the two inputs go to the output, and of course you can scale it up to a 4 or an 8 or a 16 input. And as you scale up the number of inputs, the number of select bits increases. That's the log base 2 of the number of inputs, right? But in Verilog, you can implement a multiplexer very easily by using just the concurrent assign statement and the ternary operator. So basically you say assign y equals s, s being the select, that's the decision, right? That's the true or false. If s is true, I want to put d1 into y. And if s is false, meaning my select value is 0, I want to route d0 to y. So this just creates an option, a switch block basically, right? I can decide which of these two things I want to send. And by the way, this is basically how FPGAs work internally, because in FPGA, you put all the logic gates down in an FPGA, and you do that just by writing a RAM. Every logic gate is created as a RAM because a logic gate is a truth table, and a truth table is just a RAM. It's just a table. A memory is a table, a truth table is a table. So by setting up tables, small tables called LUTs, you can create configurable logic gates, right? But the real magic of an FPGA is not the LUTs, is the fabric, the wires. How do you connect the LUTs in an arbitrary pattern? Well, that's done essentially through multiplexers. So when you configure an FPGA, when you program an FPGA, one of the phases of that is setting up the LUTs, the logic tables. That's when you're selecting where you want to put each one of your gates on the FPGA. That's called placement. And then the routing part is where you select all the muxes that connect the gates together, right? So every mux, the mux is a way to programmably connect wires together, right? But you can also build muxes on top of an FPGA additionally, which is what we're going to do. So our CPU, when you have a RISC-V, in the RISC-V instruction set, you can add two registers or add a register intermediate. That decision, basically what goes into the second input on the ALU, is done through a mux, right? So you're going to have a lot of muxes in there, and muxes are done with ternary statements, so you have to be comfortable with putting these ternary statements in. Like I said, it's a very obscure feature of C, but a very common feature of Verilog. Okay, I think that's about all the time I have. I think I've covered enough. I believe I've covered enough material for the quiz. The quiz just asks basic questions about SystemVerilog. If you have any other questions, feel free to contact me, and we'll see you on lab on Wednesday. Oh, the TAs will describe the lab assignment in lab, because I didn't get to that today.